This app helps you to understand the concept of p-values in hypothesis testing for average. So before we discussed the artificial case with coins, and also we discussed how to do the hypothesis testing for proportion. Now let's talk about average. Okay. So what do you see here? This plot shows you a distribution of the population. So these are values. So you have a very huge population, and then you have a sample. You can see the sample size is 5 in this case, right? So this is the sample. Why you see 4 points instead of 5? Because it happens that 2 points are very similar here, right? The dashed line shows you the average of your population. So you can see its average is 100. So in this case, we are talking about chloride in water. For example, we have different parts of the lake, and then we have some variation of the chloride in different parts of the lake. This is standard deviation of my population. However, you can see that if I take a random sample of size 5, you can see that the average of my sample is a little bit larger than the average of my population, right? And the sample standard deviation is also larger. And then this is the average of my sample, and then you can see that every time I take a new sample, I never have average the same as the population average. For example, in this case, you can see the distance is large. I have approximately 3 standard deviations larger in this case, right? Sometimes this distance is small, sometimes it's large. The problem is that you don't know the population average. You know only sample average, okay? So the question is, how far your sample average can go from the population average? That's what hypothesis testing allows you to answer. For example, in my case, I believe that average of my population is 100 or more milligrams per liter. So in this case, the null hypothesis is true, right? Now the average of my sample is 99. So it's smaller than this one. So I believe it should be 100 or more. I have smaller than 100. So my sample kind of extreme for my null hypothesis, right? But because it's a sample, because it has this uncertainty, it's likely. I can have a sample with this average, although the null hypothesis is true, right? How likely? That's the p-value that tells me that, right? Again, I have a distribution. In this case, I use t-distribution based on the population, the null hypothesis, the population mean that I believe it's correct, and also based on the sample standard deviation. So therefore you will see that although the peak of this distribution is always the same, the variation will be different. It depends on the sample standard deviation. Then look, this is my population, this is my sample. I believe it should be 100 or larger, so I believe that it should be in this direction. So any value in this direction will be more extreme, right? So therefore, the p-value, it's a chance to get a sample as extreme as mine, or more extreme for the null hypothesis, and that's exactly this area, right? And that's what you can see here. It's the p-value is 20. So 20% chance to get a sample of this average 99, or maybe even less, if the average of my population is 100. So in this case, it's a pretty big chance, right? And if I take a new sample, you can see in this case, the sample mean is very close to the population mean. I believe it should be 100 or larger, and then that's why you can see the p-value is almost 50%. Okay. So take a new sample, Now how often sample average will be too extreme? For example, if I compare p-value with 5%, right? It's exactly 5% of the time. So if I take a lot of samples, you will see that 5% of the time I will reject null hypothesis. In my case, you can see it's 9% of the time. You can see that 6 times, so I took 62 samples, and 6 times the p-value was too small. So it means that the average of my sample was too far away from the average of my population, considering the significance level 5%. So I rejected my null hypothesis 10% of the time, although I know it's correct. When it's 5, when you take a lot of samples, so if I keep going, you can see that sometimes it's red. Red means it's the p-value is small. If I keep going, this value will be approximately 5%. If I, for example, take thousands of samples, okay? So what does it mean? Again, it means the following. If you work with 5% significance level, when you take a sample, you have 5% chance to get a sample which is too extreme for a null hypothesis, although the null hypothesis is true, and therefore you will reject it, but it will be a mistake. So you will do it, you will make an error, type 1 error, right? So once again, take this 5% value carefully, right? And then the rest is similar to what we discussed in proportion. When you change the tail, it means you change the direction of extremeness. So now you can see that I believe the average of population should be 100 or less. And therefore, every time I have a sample with whose average is larger than the given, this one, it will be even more extreme. So the p-value will be computed using the right tail, not the left tail, right? And also the sample size influence very much. You can see that the larger sample size, the smaller uncertainty. But this is still the same. So if you have a large sample size, you still will have 5% chance to make this rejection of the correct null hypothesis. So if I repeat this many, many times, you will see that in 5% cases, I will reject the null hypothesis, although I know that in this case, the null hypothesis is true, right? So you can see that in this case, for example, I took 143 samples, I got 3% rejections. But again, if I keep going, like take a really big number, like thousands times, then it will be 5%. But once again, every time you take a sample, if you work with significance level 5%, you have 5% chance to make this wrong, incorrect decision. So you reject null hypothesis, although the null hypothesis is true. Okay. So that's how it works for mean.